So first off, interactive query speeds. This is a topic I'm not going to belabor too much because I actually spent most of my time at the last Druid Summit talking about this topic. So if you're interested in hearing more about it, check out that talk. I also talked about it in more detail at ApacheCon, I think 1 or 2 weeks ago. And that video is not online yet, but it should be online shortly. And so check that out as well. But suffice to say, the short version of that is that Druid uses a lot of best practice techniques in the database world to achieve high performance, compression, indexes, operating on compressed data, late materialization. It's really important to understand, at least at a high level, how this stuff works if you're going to get best performance, because it actually directly impacts how you might want to partition your data, how you might want to order your data, how you might want to model your data. So it helps to have a mental model of how the database works when you're thinking about how to store and lay out your data. This is a little bit more on that topic. Part of, I guess, a little bit more of a flavor of how things work. In Druid, we're a columnar store. So this is a one slice of a Druid table. This little picture here is 8 rows. And there's a time column with 8 rows in it. And every column you see has 8 rows in its data section. Again, check out some of these other talks if you're interested in details about how a query might be executed on top of this. But for now, the point I want to get across is just having this mental model in mind is really important. Okay, so putting the performance stuff aside, let's spend a little bit of time talking about some of these other properties. So, the first one I want to talk about is this always online property. So this is a picture, a sort of schematic picture of Druid's architecture, and I wanted to talk a little bit about how this architecture enables this always online property. So the first thing that we see here is that on the data server, there's 2 of them. There's actually more than one of everything. We just didn't have room for them all on the slide. But everything here, there's more than one of. Everything here is highly available. There's 3 basic kinds of servers in the system. Data server, which is the majority of servers in the system. They do what they sound like. They store all your data. They compute on your data. Query server, which is what handles queries and then fans out queries to the data servers. And then master servers, which they're more of a scale up than scale out. You're going to have 3 of them for high availability, but there's not really a strong reason to have more than 3 of them. Because it's just a high availability thing. It's adding more of them doesn't give you more capacity or anything. Each of these bits has a way that it enables fault tolerance. So for example, the query servers are designed to be stateless and put behind a load balancer, and you can run as many of them as you want. That's pretty straightforward, and it works the way that a traditional web server would work in terms of high availability, just spin up more of them. Data servers are a bit more complicated because they are stateful. They're not stateless like the query server is. But they're designed for fault tolerance in that they have this deep storage concept. And deep storage is basically a backup of all the data. And the deep storage is, as data is being ingested into Druid, it's being continuously written in deep storage. And the data servers are able to pull data from deep storage if they need to increase replication of it. So even if you lose all your data servers, you can actually create new data servers that are blank, and they will rehydrate themselves from deep storage. So that's an extreme case of fault tolerance. But in the less extreme case, where you lose a single server or a couple of servers, something like that, the remaining servers are going to be able to pull the data that those servers had from deep storage, even if all replicas have been lost from the data server cluster. This is a great property. It happens automatically. It happens in the background without you having to do anything, and it enables the fact that these tables are always going to be online. Finally, on the master server, they use a leader election protocol that's mediated by Apache Zookeeper, and that means that at any given point, one of them is going to be active and leading the cluster. If that one is lost, then a new leader will be elected. Finally, I want to talk about how rolling updates work, which I mentioned can be done without downtime. Pretty straightforward. You just update one server at a time. And the protocol is designed such that if you update all the data servers first, one by one, then all the query servers, then everything is cross-compatible. And so the older query servers will be able to talk to the newer data servers, and it's okay to have them mixed. Stay on this picture for a bit, but masking off parts of it that are irrelevant to this point, I wanted to talk about loading fresh data from streams. So the way that we load data in Druid is through these indexers that run on the data servers. And indexers are responsible for pulling data. Druid's got a pull-based model. They will pull data from either batch locations or stream locations. And when they're pulling data from a stream, like Apache Kafka or a cloud-based streaming system, what is going to happen is the broker will be able to query them and able to query that data that has been pulled from the stream and hasn't been written to deep storage yet. And that's generally going to represent about an hour's worth of data. And if that data is lost, that's okay. It hasn't been written to deep storage yet, but we can reread it from upstream. We can reread it from Kafka by rewinding, and we actually store the Kafka offsets together with the committed data, the committed metadata, so we're able to always restore anything that's lost like that. And because the query broker is able to query directly from the indexer things that have been read from a stream but haven't been written to deep storage yet, that's what enables the ability to see what's happening fresh. We don't just see the hour-old stuff that's been pushed out to the historical system. We see things as they're being loaded in the indexer. This also helps with efficiency because you see sort of schematically here, the historical has this highly optimized data format. The indexer actually doesn't. The indexer has a format that's designed more for being able to insert and update quickly as opposed to being able to read quickly. And so you sort of have this write optimized form on the indexer and the read optimized form on the historical existing simultaneously and automatically getting rolled over into each other. Next, I want to talk about quality of service. So quality of service is, sorry, one second. Yeah, I want to talk about quality of service. So I've got a picture here of a carpool lane. And I think a carpool lane is a good metaphor for how we think about quality of service in the Druid world. And I mentioned earlier that if you have a lot of load, you have a couple options. You can either scale to meet that load, or you can use prioritization. And the carpool lane system is how a highway prioritizes traffic. We decided as a society that we want to prioritize folks that are carpooling. That we want to encourage carpooling, and so we want to prioritize that traffic. And so we built a special lane for them. Similarly, as a Druid cluster operator, we can decide that we want to prioritize certain workloads and we want to build a special lane for them. A car, just like on a highway, if you're driving in a carpool, you can drive in any lane you want. You don't have to be in the carpool lane. You can be in one of the other lanes too. But you can be in the carpool lane. You have the option, and folks that are not carpooling have to stay in the other lanes. In Druid, we've got a laning concept that works pretty similarly. So you imagine having a fast lane and a slow lane. And if you are a high priority workload, you can use any lane. And if you are a low priority workload, you can only use the regular lanes. You can't use the special fast lanes. And that ensures that there's a certain amount of capacity that's reserved essentially for these higher priority workloads. And one thing that's important to note is that the capacity that we're reserving is related to how many queries can run concurrently, but not how much data can be processed concurrently. And that's an important point that this next slide will help illustrate. So going back to this picture, the way that the quality of service stuff works in Druid is if you think about the broker is able to handle a certain number of queries concurrently. Let's say it's 50. It depends on your configuration, but 50 is a relatively typical number to use. And what that means is that there's 50 queries that can be running at one time. Let's say that you've decided to reserve 10% of that for high priority workloads. What that means is that at most 45 queries can be running that are low priority. And even if that's happening, we'll have five slots essentially open for high priority ones. At the historical level and the indexer level, we have a different way of applying priorities. At that level, rather than having lanes, we prioritize this processing of individual segments, and those are interleaved. And this is actually a really important point because it means that a single low priority query actually can use the entire resources of the historical and indexers on the data server. It's not limited to 80% or 85% or whatever. It can use 100% of the resources in the data servers. But it will be preempted if a higher priority query comes in, and it'll have to wait for a bit. And so that means that we've created a system where we're doing quality of service in a pretty nice way, where even low priority queries can use all the resources. Any query can use all the resources of the data servers, and we're just limiting how many concurrent ones can run at the lower priority. So that's quality of service. It's very important for app building because it's like I was saying, it's an important part of how you handle heterogeneous workloads without breaking the bank. And finally, price performance. Price performance is really important. What we found is that independent benchmarks like this one, Druid with its design for performance, storing an optimized copy of things, having these secondary indexes, doing all these things I mentioned earlier, has double, triple digit performance advantages over the query engine type stuff. And this is why people choose to use online databases like Druid instead of these query engines for building applications on top of. We see similar things comparing Apache Druid with cloud-based data warehouses, which I think makes sense. Because internally, those cloud-based data warehouses work sort of like query engines, querying things out of data lakes. And what this all does is it comes together. Wrapping up, this all comes together to build a system that's able to build a nice data application on top of, build something that's really high performance, so high performance that people are happy to engage with it, and increase the engagement of data throughout your team, which is really the whole point of building a data app in the first place. And to do that without breaking the bank, by having these tools for quality of service, having really good price performance. So you don't necessarily have to, you can scale your way out of really any load issue you run into because it's a scalable system. But we also give you a lot of tools to not necessarily have to scale your way out of it and to make do with what you have and still get good results.